Have you ever wondered what young stars, such as our Sun, may have looked like in their early years, 5 billion years ago? How new stars are born from remnants of old stars. These studies are very important in the astronomy, as they provide insight into our roots in the universe. And if you're also interested in the answers to these questions, then you'll be shocked by the new breathtaking photos taken by the James Webb Space Telescope. The most recent stunning images shows jets of star matters blasting from a very young star's poles and flying through space at supersonic speeds, as seen in incredible details taken by NASA's powerful James Webb Space Telescope. Join us today as we learn more about this incredible discovery made by the JWST and why this image is so important for astronomy. The James Webb Space Telescope continues to deliver on the promise of incredible images. Webb is solving mysteries in our solar system, looking beyond to distant worlds around other stars, and probing the mysterious structures and origins of our universe and our place in it. Webb is an international program led by NASA with its partners, European Space Agency and the Canadian Space Agency. The most recent pictures of the protostellar outflows of Herbig-Haro 211. Said that way, even with the image that are seeing right now might not tell you much. Let's put it another way. What you are seeing is the output of a very young, small star into the universe. Big jets of material that are hitting other cosmic stuff, creating a turbulent interaction that shines in this beautiful composition. An outflow from a Class 0 protostar, an infantile replica of our Sun, when it was just a few tens of thousands of years old, and with a mass of only 8% of the current Sun, is visible in this view of HH211 from NASA's James Webb Space Telescope. It will eventually grow into a star, similar to the Sun. Bright nebulosity patches known as Herbig-Haro HH objects are linked to young stars. They are created when fast-moving, nearby clouds of gas and dust meet with narrow jets of partially ionized gas ejected by stars. Herbig-Haro objects are frequently observed around a single star, aligned with its rotational axis in star-forming regions. Most of them lie within 3.26 light-years of the source, although some have been observed several light-years away. The lifespan of HH items is only a few tens of thousands of years. They can undergo noticeable changes over periods of a few years as they move quickly away from their parent star and into the interstellar gas clouds. A growing star first begins to form inside a huge cloud of gas. Local instabilities cause the gas to start collapsing, leading to the core of a young star to develop. The young protostar can't radiate heat well when the gas becomes denser because of the growing opacity. As a result, the cloud warms up, stabilizing it and preventing it from collapsing. The young protostar cannot fully absorb the additional gas that is still falling towards it. The gas forms a rotating disk around the protostar. Some of this material is ejected by the young star along its rotational axis from two bipolar jets. Herbig-Haro 211 is being studied by the Webb Telescope, since the specifics of this process are still being determined. In the constellation of Perseus, HH211 is one of the nearby Herbig-Haro objects and is just around 1,000 light-years away. The Webb has difficulty seeing the material in the jets. The jets, on the other hand, excite molecules in the surrounding gas, such as hydrogen, carbon monoxide, and silicon monoxide. These energized molecules emit infrared light, which was captured by the JWST's NIRCam instrument. But how did Webb manage to capture such a stunning image? One of the reasons for the JWST's creation was to study newborn stars. Young stars form within vast clouds of gas, and as they grow in size and age, they blow away some of the gas and reveal themselves. When the stars eject the gas, they become much easier to observe, but it's too late to examine the newborn protostar. With its incredible infrared observation capabilities, the Webb Telescope can see inside these massive clouds to observe young stars and their HH objects at work. The Jwst reveals more information in these stellar objects than ever before. Its image of HH211 has a spatial resolution that is nearly 10 times that of other photos of the same object. In the image's upper right and lower left corners, bow shocks has been detected. The James Webb Telescope has the capability of revealing some of the knotty clumps in the visible bow shocks. We can also see the energetic jets coming from the star. They have a symmetrical, wiggly look, indicating that the young star could be a binary star. The majority of HH objects are born from binary stars. The wiggling is most likely caused by stars interacting gravitationally with one another. Scientists found the speeds involved with these jets, shock waves, and surrounding debris using these photographs and study, paired with older images. The innermost regions of the HH object outflows are traveling at speeds ranging from 80 to 100 km per second. This sounds fast, but is actually slower than similar outflows from older, more evolved stars. At the bow shocks, where the outer parts of the outflows collide with the surrounding gas, speeds are much lower. Because the material in the jet strikes the gas so slowly, there isn't enough energy to split the molecules apart into their constituent atoms and ions. As a result, the researchers concluded that the jets are molecular in nature. In a more evolved protostar, the higher velocity of the jets would break the molecules apart. Researchers discovered that jets from young stars are slower and richer in chemicals by analyzing data from HH211 acquired by the Near-Infrared Spectrograph instrument. This is compared to the quicker jets that erupt from older stars. HH211 belongs to a class of objects known to change quickly, with gas swirls disappearing only a few years after detection and new ones appearing in seemingly empty regions of space. This is an amazing discovery. It shows that early protostars and their slower jets are likely to enrich their surroundings with complex molecules. Some of these chemicals serve as the foundation for even more complex chemicals, some of which are linked to the formation of life. Both Webb and Hubble have looked at several of these fascinating young systems to better understand how stars come to be. The level of detail Webb captured is unprecedented. This is another example of how Webb can unlock further secrets of already well-studied cosmic structures. The James Webb Space Telescope has given us beautiful glimpses of space through images that are brimming with galaxies, planets, and alien worlds that formed right after the Big Bang. With James Webb Space Telescope, scientists hope to better understand the earliest galaxies and stars that can help get humanity closer to the origins of life as we know it. I hope you enjoyed this video. Don't forget to hit the like button and subscribe to our channel for more interesting space-related content. Thank you very much for watching, and I will see you in the next video.